So we're going to be talking about weak acids and strong base titration curves today, and what those look like. So on the screen, you can see that um, we have sort of the difference between the weak acid and the strong acid. Previously, we talked about how the strong acid kind of stays at the same, increasing slightly, and then boom, hits that equivalency point, and then you are in the basic phase. A weak acid, A, starts at a higher pH, so weak acid, so it's not going to be able to have a stronger pH than a strong acid. And then it's much more of a gradual rise as it goes up. Um, this region right here, from here to about right here, this is where we have our buffer region. Remember that buffers are when you have a weak acid and its conjugate base inside of the solution. So um, let's start talking about what that means. So we have sort of these areas on the graph here. So we have pH graphed along our y-axis, and then volume of the base added. This is a weak acid. So at the beginning, how you're going to do these calculations is at the beginning, we haven't added any base yet. So the only thing in the solution is the acid. So in order to find the concentration of that, you would do like a normal weak acid pH. So you do a quack table and you end up getting like x squared over the concentration of the acid, where x is the concentration of the H plus 1 ion. In the solution, we would have, let's call it HA as our sort of general term for a weak acid. So we have only weak acid, but we know that it's not HA together. They actually dissociate slightly. So it's actually an H plus ion and an A minus ion in that solution. All right, so let's go ahead and do sort of an example problem of what we're talking about with the titration. This is from our notes. This is exercise 12. It's the last thing in our notes. So what we're going to do is we have a 50 milliliter sample of 0.1 molar HCN. It gives us the Ka is 6.2 times 10 to the negative 10th, and it's titrated with 0.100 molarity NaOH. So this is our weak acid, and this is our strong base that we're titrating with it. And our goal is to calculate the pH for all of these things. So the first thing we're going to do is before the titration begins. We just talked about how before the titration begins, there is only the acid in the solution. So we are going to do a quack table. So we are going to use the dissociation of the acid plus water. This is aqueous. This is a liquid. It's at equilibrium with H3O plus, which is aqueous, plus um, Cn minus, which is aqueous as well. So quack table. Um, when we start, we have 0 of this, we have 0 of this. Our concentration is 0.100, and we don't care about the water. So we have minus x, plus x, plus x. So this is going to be 0.100 minus x. This is going to be x. This is going to be x. Now, in order to solve this equation, what we're going to do is we're going to plug this into our K expression. So we have Ka is equal to the concentration of the H3O plus times the concentration of the Cn minus divided by the concentration of the HCN. Once again, water doesn't show up because it's a liquid. Now we start plugging in numbers. 6.2 times 10 to the negative 10th is equal to the term x times the term x over 0.100 minus x. This minus x here is going to be negligible, and that's due to x being much, much smaller than 0.1. Now we've used our calculator in order to solve for x. We have 2.6 times 10 to the negative 10th times 0.1. square root of that answer. We get x equal to 7.8, 7.9 times 10 to the negative 6th. And that's molarity because that is the concentration of the H3O+. Now, in order to find pH, we do the negative log of that. So negative log of our answer, we get 5.10.